Hello, and welcome to the next set of notes and discussion on covalent bonding. We've already talked about Vesper, but now we got to get into the effects of lone pairs as well as polarity. So, the whole point of Vesper, valence shell electron pair repulsion, is to keep and make the bonded pairs of electrons as far apart from each other as possible, as well as lone pairs. And due to that repulsion of these electron groups, or sometimes called the electron domains, that repulsion is what brings about different shapes that exist from our both electronic as well as the molecular geometry. So, quick review of our shapes. Linear geometry, again, this is assuming no lone pairs. And then trigonal planar, 120 degree bond angle. Tetrahedral, 109.5 bond angle. Trigonal bipyramidal, both 120 and 90 degree bond angle. And then lastly, octahedral, being a 90 degree bond angle everywhere. So again, these shapes and these angles correspond to both the electronic and molecular geometry, with the assumption there is no lone pairs on the central atom. Another way of looking at octahedral, just thought I'd share it with you. All right, so the effect of lone pairs, what are they doing? How are they affecting the molecular geometry? And how do they support these other shapes occurring? Well, at the end of the day, lone pairs occupy more space. They take up more room of electron density than a bonded pair of electrons. Remember, bonded pair of electrons are shared between two atoms. They aren't really free to move, so to speak. But a lone pair of electrons has the entire orbital existing with that singular atom to kind of move around and take up space. So lone pairs, again, take up more space, which means the repulsion is going to be greater. So if we want to compare repulsive forces, we can look at the following. A lone pair being repelled by another lone pair is a greater repulsion than a lone pair having repulsion with a bonded pair, which again has greater repulsion when looking at a bonded pair repelling another bonded pair. So these three different ways that repulsion can occur, dealing with lone pairs and bonded pairs, is what plays the role in creating other shapes that exist. And as we kind of saw earlier, it's going to affect the bond angles. It's going to make them smaller than expected. Now, again, our bond angle is based on bonded atoms only. Any questions on this? Okay. So, for example, let's take ammonia. On the left-hand side, we can see from the electronic geometry, it's tetrahedral, 109.5. But because it has a lone pair on the right-hand image, giving us a actual molecular geometry of trigonal pyramidal, that lone pair has a greater repulsion with those bonded pairs of electrons, more so than the bonded pairs between each other. So the bond angle changes, or it gets smaller, because those hydrogens are pushed closer together. Questions on this example? Okay. To further it, again, here's water. On the left-hand side, it's electronic geometry, tetrahedral. Same as ammonia, and the same as methane, CH4. All of them electronically are tetrahedral. But if we look at a water molecule from a molecular geometry standpoint, it's a bent structure. There are two lone pairs on oxygen. They're going to repel each other, the lone pairs, a lot. But then those lone pairs are going to also repel the bonded pairs between the hydrogens and the oxygen, forcing those hydrogens closer together. Remember, two lone pairs to each other greater repulsion than two bonded pairs, which again changes the bond angle from a 109.5 to a 104.5. So we can see as we're adding more electron pairs, the bond angle is changing. Quick look back, one lone pair. I believe this should be 107.5, so I apologize for that. And then we look at two lone pairs. Questions regarding the effect of lone pairs on our molecular geometry. Okay, which brings us to polarity. The only way we can ultimately figure out the polarity of molecules, we have to know its molecular geometry. Without one, it makes it very difficult to do the other. So, at the end of the day, for a molecule to be polar, it has to have polar bonds. If all the bonds within the molecule are non-polar, it's not going to be a polar molecule. So, gotta have polar bonds. Now, how do we figure out if a bond within a molecule is polar? Well, that comes down to our electronegativity difference. We know the trend of electronegativity. Again, we're not using any numbers here. It's just that trend. Remember, fluorine, the most electronegative atom. If you have a polar bond, you have a bond dipole moment. The dipole moment shows the direction of polarity. Remember, with an arrow and a positive sign on the opposite end of that arrow, that is a measurable number that we can get and then compare it to other parts of the molecule. Also, to be a polar molecule, you have to have symmetry or asymmetrical shape. Symmetry plays a very big role, either being symmetrical or being asymmetrical. Our purposes here, we want to be asymmetrical in order to be polar. That asymmetry kind of comes from the vector addition. All of our dipole moments, they are vectors. They have magnitude and they have direction. When you add up all of the dipole moments, no, you're not going to do that for this class, but when you do, if they add up to 0, you're nonpolar. But if they add up to some number and a direction, meaning you have an asymmetrical shape, the vector addition also proves it is a polar molecule. Polarity affects intermolecular forces of attraction as well. We're going to get into IMFs more so next semester, but again, polarity still plays a role, and since we're talking about bonding and polarity, we'll make a little note of it here. Polarity can affect boiling points, solubility, properties. We have the IMFs that control these as well, but polarity goes along with it. We know from solutions, like dissolves like. So if I'm trying to mix two things together, if they have similar bonding characteristics, they should mix with each other. If they don't, they shouldn't. Just think oil and water. The non-bonding pairs, think of it as lone pairs, same idea. They're really going to affect molecular polarity. If you have lone pairs, chances are your molecule is going to be polar. Now, I'm not saying in always. Just because you have lone pairs does not automatically make you polar. It still comes down to the shape of the molecule, which is what you're going to get from VSEPR, and then you can determine symmetry based on that shape. Any questions on polarity? All right. Thank you very much.